Good morning. Last time I suggested that it might be possible to set up self-consistent and unambiguous rules for multiplying rank 3 matrices. So I spent a large part of the following day trying to find just the right conventions to do so. My final version of matrix multiplication is based on drawing a particular set of directions in the matrix dimensions, preserving the old dimensions of down and right. So A, B times C times D would be equal to AC, AD, BC, and BD. And then also adding a third dimension, fourth. So, but instead of drawing this one as like A, B, and CD, I'm going to draw it this way. Equals A, C, A, D, B, C, and B, D. I wanted the down right expression of the third dimensional matrix to preserve all of the properties that it had before. For instance, here a 2 by 1 times a 1 by 2 matrix gives a 2 by 2 matrix. Let me go back one step. I've just realized that how awkward it's going to be to call the third direction the fourth direction. I think maybe I think despite the extra syllable, it should be called the forward direction. So we have down, forward, and right. So instead of adding the third dimension after the other two, I am adding it between the other two. So this is going to be called a 1 or a 2 by 1 by 1 matrix. This one is a 1 by 1 by 2 matrix, and it provides a 2 by 1 by 2 matrix. The forward direction, the 1 by 2 by 1, or 1 by 3 by 1, or whatever you want to use, can be drawn as a cylinder option. Actually, like that. You don't want to draw both ends because that makes it kind of ambiguous. The front end should be exposed to view so that it's clear that you're looking at it as it goes into the background. Now, if all three of these directions are drawn together, it forms sort of a street sign. So, like, with downward being direction 1, forward being direction 2, and right being direction 3. Direction 1 is the 2 by 1 by 1 matrix, or n by 1 by 1. Direction 2 is the 1 by 2 by 1, or 1 by n by 1. And direction 3 is the 1 by 1 by 2, which is 1 by 1 by n. Of course, if you're wondering why I'm introducing n's here, it's because the dimension of the vector space could be 2, 3, 4, whatever, etc. So n is the dimension of the relevant vector space. Okay, so in the conventions I've worked out, there's really only one more step to go after that. Recall how matrix multiplication works for horizontal and vertical matrices. If I multiply a horizontal vector times a vertical vector, I get a scalar. This is a dot product or a inner product. And I will denote that now instead of, or as a shorthand, I will, this is a 3 by, a direction 3 times a direction 1. So I'll just write 3 times 1 right there. Gets a scalar. On the other hand, if I just write it up here, I guess, if I multiply a vertical times a horizontal, I get that's an outer product. And so that'll give us a 4 by 4, or I mean a 2 by 2 matrix. So if I multiply 1 by 3, the direction 1 by a direction 3 in that order, I get an outer product. And what I'm going to do is I'm going to maintain those so that outer products are 1, 3, 3, 2, and 2, 1. And the inner products will be just the opposite, basically. 3, 1, 2, 3, and 1, 2. So let's show some examples. Direction 1, 3 we've seen. Let's look at directions 3, 2, which is this times this. Direction 3, 2 is going to be an outer product. AB times CD is going to end up being basically a square matrix in that direction with AC, BC, DA, and DB. While the inner product version would be, if we had AB times CD going this way, that would just be AC plus BD. So that's direction 3 times direction 2. This one's direction 2 times direction 1. This is also a 1 by 1 by 2 matrix multiplied by a 1 by 2 by 1 matrix. And you'll see that this no longer has that feature that we were able to have with the two-dimensional matrix where saying these two terms had to match. But it does give you a 1 by 2 by 2 matrix. So that's 3, 2, and 2, 1. Let's go on to 2, 1, and 1, 2. 2, 1 is direction 2, which is the forward direction. I'm just going to draw that with A, B times direction 1 is coming down, so times C, D, and it's going to give us something kind of like this with AC, BC, DA, and BD. I should have written AD and BD. AD, BD, and 1, 2 would be AB, CD equals, it ends up being AC plus BD. Now, how can you remember which version of matrix multiplication will lead to an inner product and which will lead to an outer product? I do something with the right-hand rule. With this direction 2 times direction 1, you'll find the cross product of forward cross down is left. It came out awkward, so I'll draw a little bit more structure in there so you can see what I was thinking with those arrows. Alright, so forward then down, the cross product of those two is to the left. Left is not down, forward, or right, but if you do the cross product in the other direction, if you go down then forward, the cross product of those is right. And I'll just try to fill in a little bit more dimensionality to that structure as well, and so you can see where those are going. And anyway, that product is right since it is in the set. If the direction of the cross product of the two, I should say directions, these aren't really the two, I'll call it tensor directions, is in the set, then it's an inner product. And if the direction of the cross product of the two tensors is not in the set, then it's an outer product. So let's go back to this one and see the outer product of right then forward is up. And up is not one of the things. But the outer product, or the cross product of forward and right is down. Down is in the set, you get an inner product. Same way with way up here. The dot product of, the cross product of down then right is back toward you. So it will give you a cross product or an outer product. And if you go to the right then down, the cross product of right then down is forward, and forward is in the set, so it would give you an inner product. Okay, so then what about notation? I think I found that if I'm writing on paper, I'd probably go ahead and use this notation, as bulky it is, with the circles and the ovals, to denote solid three-dimensional objects to convey the dimensionality of the matrices. Alright, but let's try to make this as backwards compatible as we can. This 1 by 2 matrix, 1 by 2 by 1 matrix would look like this, and the 2 by 1 matrix would look just the same way as it always has. And then the 2 by 2 by 1 would look like AC, BC, AD, BD. So the 1 by 1 by 2 and 2 by 1 by 1 matrix will look just as they always have, but the 1 by 2 by 1 will have the extra parentheses. Let's go up to this other example that we did earlier. The AB times CD is going to look like what? This AB times CD would be equal to AC. Wait, it's gonna look like this. AC, AD, BC, BD. Okay, so now we've got outer products and inner products. Let's move from there to imagining multiplying square matrices by vectors. Let's begin with the ones we already know. We've got square times horizontal, square times vertical, uh, vertical times square, and horizontal, and horizontal times square. So this one is illegal. In the old way of doing it, we'd say it's a 2 by 1 by multiplied by a 1 by 2, 2 by 2 times a 1 by 2, and it's illegal because this number doesn't match this number. So in two-dimensional matrix multiplication, the reason the square matrix doesn't multiply with the horizontal is because the row size of the first matrix doesn't match with the column size of the second matrix. The row size here, which is 2, doesn't match with the column size, 1. Now I'm thinking of some possibility of a new mnemonic, such as you can't multiply a down-right matrix by a right matrix. Down right times down is fine, and right times down right is fine, but you can't do down times down right. So if that mnemonic were established, we'll need to learn the other two legal versions of the square matrices. So recall that that's direction 2, then direction 1, and then direction 3. Down right is 1, 3, 3, 2, and 2, 1. Those are the legal ones. This one's going to be called down right. This one is right forward, and this one is forward down. So the legal matrices would be the down right times down, or right times down right. The legal matrix for right forward would be forward, or right forward, right. And the legal matrices for forward down would be down, and forward down, forward. The illegal matrices would be down, right, with whatever is repeated, so, or down right, right, etc. So I got a list of legal and illegal, and we kind of know what these are going to do because we have a precedent from the two-dimensional case. Something we don't have a precedence for is what if I took down right times forward, or forward times down right. And I think what I would get, well, let's try down right, A, B, C, D, and at the risk of repeating variables, A, B, C, D times E, F, different F, so I could lowercase that, I guess, but yeah, let's lowercase it. A, B, C, D, E, F. Let me just write this as, I'm going to say AC equals G, AD equals H, and I'll just put in some letters for this thing so that I don't have to write too much. And then this one's going to come up this way. EF. So I would think that multiplying these two things is going to give us a GE, HE, IE, JE, and then I guess maybe I should write it like this. GF, HF, IF, JF. That would be the logical way, because that's what's going to come out of this, I think. If we have G, H, I, J times parentheses, parentheses, EF, that's going to give us GE, GF, HE, HF. Yeah. IE, IEIF, and JEJF. Which is a 2 by 2 by 2 matrix. Now I think that all of these will be the same. I can't see any reason that down, right, forward, down, right, forward would not equal to forward, down, right, and forward, down, right. I think as long as you're making a 3 by 3 by 3 matrix, these are going to tend to be associative. Well, let me confirm associative. I don't know if they'd be commutative, but surely associative. I'm going to leave the commutativity issue for some other video, and just ask, while I'm asking that question about commutativity, I'm going to bring up one elephant in the box or in the room. What about multiplying 2 by 2 matrices in one direction by 2 by 2 matrices in another direction? This would be a forward down times a down right, for instance. I have a feeling that's going to be illegal because we've got the down and the down next to each other. But if I reverse that and moved this over here, that one might be legal. And if we did the right forward matrix times the down right matrix, I think part of the reason that these are legal is that they preserve the sense of the matrix multiplication from the 2 by 2 matrices, where you would sum along the horizontal of the left matrix and down the vertical of the right matrix. And so if this RF times DR was to form a 4 by 4, 3 by 3 by 3, or 2 by 2 by 2, I should say, it would go, this spot would be this times this. 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 And this spot would be this times... Actually, come to think of it, I'm out. I don't think that's going to give me a 1 down there, is it? So I can say right forward times down right gives us a right, or gives us a forward right, or I mean gives us a right forward. So we should probably expect each of these down right times forward down to give us a two-dimensional matrix in the let's see, we kept one of them, didn't we? Might be easier to see these if I write this as direction 3, this is direction 2, down is direction 1, right is direction 3, and that came out to be equal to a direction 3, 2. So if that pattern holds, then the 1, 3 times 2, 1 would give us a 1, 2, and the, what am I saying, a 1, 3, I mean, and the 3, 2, 1, 3, 2, 1, 3, 2, 1, 2, 1 times 3, 2 would give us a 2, 1. And the final consideration to make is whether 1 by 2 by 2 times 2 by 2 by 2 matrices, or 2 by 2 by 2 matrices times 2 by 2 by 2 by 1 matrices would multiply. So I think since I preserved matrix multiplication in the old down and right direction, the clear rules can be established for three-dimensional matrix multiplication. What is legal, what is illegal, and what ambiguous result you would get in every legal case. So I'm not entirely sure how much use this is going to be in figuring out Einstein notation, but as I pursue the covariant and contravariant derivatives, I'd like to see whether they can or cannot be put into the context of three-dimensional matrix multiplication. Thank you for watching.